In the last video, we found limits using direct substitution. And we noted that direct substitution should always be our go-to technique when trying to evaluate limits. But the bad news is that it doesn't always work. Let's look at this problem, for example. Here we're asked to find the limit as t approaches 2 of 3t squared minus 7t plus 2, all of that over 2 minus t. If we try to evaluate this limit using direct substitution, we get the indeterminate form 0 over 0. But that doesn't necessarily mean that the limit does not exist. So let's see if we can manipulate this function in such a way that when we do try direct substitution, it works for us and gives us a value for our limit rather than the 0 over 0 indeterminate form. Anytime we're trying to find the limit of a rational function and we get this 0 over 0 or indeterminate form, we're going to try what's called the factor and cancel technique. That means we're going to factor the numerator, factor the denominator, and then cancel any common factors or reduce the fraction, and then see if we can use direct substitution. In the numerator, 3t squared minus 7t plus 2 factors into two factors. The first factor is 3t minus 1, and the second is t minus 2. And if we factor a negative 1 from the denominator, that gives us negative 1 times the difference, t minus 2. And we see that we have a common factor of t minus 2 in the numerator and the denominator. So we'll cancel those common factors. And that gives us the limit as t approaches 2 of 3t minus 1 over negative 1, or the limit as t approaches 2 of 1 minus 3t. Now this is just the limit of a polynomial function, and we can use direct substitution to find the value of the limit. So substitute 2 in for t. And we find that the limit is negative 5. This factor and cancel technique will come in handy when we're trying to find the limits of rational functions. And this rational function was pretty easy to look at and say, yeah, I think that numerator will factor and the denominator will factor. But that's not always the case. Take this example for instance. Here we're asked to find the limit as x approaches b of the fraction x minus b to the 50th minus x plus b, all of that over x minus b. Using direct substitution gives us 0 in the numerator and 0 in the denominator. So again, we see this 0 over 0 indeterminate form. This is still a fraction, and upon initial inspection, it doesn't look like we can use factor and cancel technique, but we can. If we study the numerator enough, we find that there is a common factor of x minus b in the numerator. So let's factor x minus b from our terms in the numerator. If we factor x minus b from x minus b to the 50th, well, that'll give us x minus b to the 50th divided by x minus b to the 1st, which leaves us with x minus b to the 49th. Now the second part is the not so obvious part. How do we factor in x minus b from minus x plus b? Let's start by rewriting minus x plus b in factored form. If we factor in negative 1 from minus x plus b, we get negative 1 times x minus b. And then if we factor in x minus b from that, we're left with negative 1. So when we factor x minus b from minus x plus b, we get negative 1. And that's all still over x minus b. Now we can simplify our fraction by canceling out the x minus b in the numerator with the x minus b in the denominator. And that leaves us with the limit as x approaches b of x minus b raised to the 49th minus 1. Now that we've simplified our fraction, let's try direct substitution. Substituting b in for x gives us b minus b to the 49th minus 1. b minus b to the 49th is 0 to the 49th, or just 0. So we have 0 minus 1, which is minus 1. And that's the limit of this expression as x approaches